Okay, here's quiz number 8. Let's take a look at number 1. So let's see here. It says, which of the following would not be considered an electrolyte? So we can look at these three here for B, C, and D. That's hydrochloric acid, sodium perchlorate, and hydrofluoric acid. And we know that these three here are indeed electrolytes. This is because when you drop them in water, they're going to dissociate into ions. And that's what makes up an electrolyte. You may think, and correctly so, that HF is a weak electrolyte, but that still means it does dissociate in water. Just perhaps not very much of it. But you put these three in water and they're going to make ions. However, this molecule here, which represents ethanol, does not dissociate electrolytically in water, meaning it does not make ions when you put it in water. It just stays the way it is. This is sort of like sugar. Sugar is another example of a non-electrolyte. So you can conduct electricity in let's say, sugar solution, but it does not form ions. So just like sugar, ethanol here is an example of a non-electrolyte. So that would be the answer to number 1. Number 2 says, which of the following acids is a weak electrolyte? So here we can go back to our discussion about how much of the electrolyte dissociates. And we know that these three, from our strong acids table, these three are strong electrolytes. Strong electrolytes. Meaning that just about 100% of the molecules are going to split up into cations and anions when you put them in water. So they're going to strongly dissociate. However, hydrofluoric acid is a weak electrolyte. Because not very much of it dissociates. Some of it still does, so it is an electrolyte. Some of it makes H plus and F minus, but not very much, because the bond between the hydrogen and the fluorine is, the fluoride is so strong that it's very hard for the water to split that bond apart and make it into H plus and F minus. But it's still possible for water to split up a little bit of it, and that's what makes an electrolyte. But it's a weak electrolyte because not very much of it splits apart. So the answer to number 2 is D. Moving right along to number 3. Which of the following species is the strongest electrolyte? So this is an example of where we can look and see which of these is going to be the strong acid or the strong base. So HNO2 is not on our strong acids table, so that's not going to be the strong electrolyte. H2SO4, that's sulfuric acid, that one is one of our strong acids, so we'll keep that one in mind. Hydrofluoric acid, well, we just talked about it being a weak electrolyte, so that's not going to be a strong electrolyte. And ammonia, that turns out to be a weak base, so it's not one of the bases that are in a strong bases table. So we come to the conclusion that B is the correct answer for number 3, because sulfuric acid here is a strong acid. So let me remind you that when we say a strong acid, that means a very large percentage of this molecule dissociates into H plus and either HSO4 minus or H2, or SO4 2 minus. So by that what I'm saying is that either 1 or 2 of the protons comes off of the sulfate, and a large majority of the molecules dissociate into ions, and that's what makes it a strong acid. So B is the answer to number 3. Number 4 says, HCl conducts electricity in water, but not CHCl3. So HCl conducts electricity in water, but CHCl3 does not. Wow, that was really hard to read for some reason. What does that tell you about the nature of the CCl bond in this molecule? Well, sort of like what we were talking about with the ethanol, these bonds are covalent bonds. And so they do not split up in water into ions. It would be very hard to make a chloride ion and a carbon cation in water. You can do it, it is possible, in other solvents, but not in water. And so since here we're talking about water, we want to be able to conduct electricity in water, which means that if we dissociate something, we want that object to make ions. And HCl very readily makes ions and conducts electricity in water, but this molecule does not. And the reason why is because of the bond strength. And so here we know from electronegativity that this is not going to be an ionic bond, so it's not A. Is it a weak bond? Well, if it was a weak bond, it would be very easy to split apart in water, so it's probably not a weak bond. Is it a covalent bond? Yes, it is a covalent bond. The carbon-chlorine bond is a covalent bond. We can do all the electronegativity differences and look them up on the tables and compare it to our scale like we did previously, and we would indeed conclude that's a polar covalent bond. And it has unpaired electrons. Well, yes, I guess you could say it does. You might have unpaired valence electrons here around the chlorine, but that's not really relevant to conductivity in solution. So really the key point here is that this is a covalent bond. And just like with the ethanol or the sugar molecules, those covalent bonds do not tend to split apart when put in water into individual ions. Okay, so the right answer for number 4 is C. For number 5, for a precipitation reaction here between iron 2 chloride and potassium hydroxide, what is the net ionic equation? So let's see here. Let's go ahead and write out the reaction. So we got iron 2 chloride and potassium hydroxide, and of course these are aqueous, and these are going to dissolve, and they're going to double displace, right? And so our cations and anions are going to switch partners, so the iron is then going to join up with the hydroxide. And we got to remember that since this is iron 2, we need 2 hydroxides. Okay, that's going to be really important. And let's see here. And the remaining partners are potassium and chloride. So we have KCl. And now to balance the equation, we have 1 iron, we need 2 chlorides, okay, and 2 hydroxides. So we can put a 2 right here. That balances out our hydroxides, the OHs, and 2 potassiums, and so we need 2 potassiums here, and that gives us 2 chlorides, and we have 2 chlorides there. So now we have a balanced chemical equation. And now let's assign phases. So this right here, we know from our solubility table, is going to be aqueous. Potassium chloride is very aqueous. It's very analogous to sodium chloride, which we know commonly as table salt. Iron 2 hydroxide, however, is our precipitate. We can learn that from our solubility rules, that iron hydroxide is the solid here in this reaction. So when we go to look at our net ionic equation, we can take the iron and the chloride and split them apart into their ions. Potassium and hydroxide can split up into their ions. And the iron 2 hydroxide here does not split up into ions because it does not electrolytically dissociate in solution. So it just sits as a lump of iron 2 hydroxide on the bottom of my beaker. And the potassium chloride here does dissociate. So here let's take a look at this equation and make the net ionic equation. So we have Fe2 plus, this is aqueous, plus 2 chlorides, also aqueous, and this is all in reactants here, plus 2 potassiums, aqueous, and 2 hydroxides, which are aqueous. And these combine to make iron hydroxide, iron 2 hydroxide. This is now solid, so we're going to leave that alone. And 2 potassiums, aqueous, and 2 chlorides, aqueous. Sorry, I'm kind of running out of room there. Okay, let's see what cancels out. So we're going to cancel out what are known as our spectator ions. These are ions that appear on both sides of the equation. Our chlorides are going to cancel, right there. Our potassiums are going to cancel. And what are we left with? We're left with the iron, that does not cancel, and the hydroxide, that does not cancel. And of course the iron 2 hydroxide here, that does not cancel because it's a solid. So therefore the correct answer is It is not this one. The reason it's not this one is because we don't have the right number of hydroxides. It turns out to be this one. C is the correct answer for number 5. So we got our iron right here, 2 hydroxides, and iron 2 hydroxide. These two do not cancel, the iron and the hydroxide do not cancel, because iron 2 hydroxide is not soluble in water. So the iron 2 hydroxide is what is known as our precipitant. So it precipitates out of solution, and that makes our net ionic equation here, iron 2 hydroxides, make iron 2 hydroxide in the solid form. So C is the right answer for number 5. Moving right along to number 6, classify the reaction type of, for this reaction here. Well, this is a molecule that is called acetic acid. Acetic acid. And this molecule here is called barium hydroxide. Okay, so we got acetic acid and barium hydroxide that are reacting together, and, well, by the name, acetic acid is an acid, and barium hydroxide, you know, is a strong base. So anytime you get an acid and a base combining, what you're going to get is some kind of a salt, so we see that here, and it is an aqueous salt, that's important, and we get water as a product in our reaction. So that indicates that it's an acid-base neutralization. But suppose you didn't recognize that this molecule was an acid, so acetic acid. Suppose you didn't know that. How could you use the process of elimination to determine which of these is the correct answer? What you could say is, well, let's see if it's a precipitation. What has to happen if it's a precipitation? I have to have a solid in my products, right? Do I have a solid here? Water here is in the liquid phase, and my salt here is in the aqueous phase. So I do not have a solid in my products. Therefore, it cannot be a precipitation. So it can't be A. Well, we just kind of determined it's an acid-base neutralization, but you might not really know if it's an acid-base neutralization, because you might not know that that's an acid. So we'll skip over that one for a second and move on to C. Suppose we thought it was C. How could we check? Well, we know that if there is an oxidation that happens, then something had to lose electrons, right? And then, of course, that's coupled to a reduction where something else has to take those lost electrons up. So when that happens, something in the reaction has to change charge. That's what's key. So something has to change charge. Let's take a look at the barium, because that might be the most candidate thing to change charge. The barium here, this ion, is bound to 2 -1 charge ions. So if it's bound to 2 -1 charges, its total charge has to be +2. Okay, and we can glean that from the periodic table as well. And here the acetate is a -1 charge, and we've got 2 of them, so we got a total of 2 negative charges. And the barium here thus also has a 2+ charge. So did the barium change charge? No, it did not. So there is no oxidation or reduction taking place. Therefore, C cannot be the right answer. So just by the process of elimination, you can determine that this is an acid-base reaction, if you did not know that that was an acid. So that's kind of how you would go about doing those. Number 7 asks us to identify the spectator ions in the following reaction. So remember how we just looked at number 5 where we did the spectator ions here? What we crossed out were ions that appeared on the reactant side and the product side. So that's all we got to look at here. Here's our chemical reaction. We got to look at ions that appear on both sides of the equation. So let's see, we got silver, aqueous silver. Do we see aqueous silver here? We do not. So we cannot cancel that out. That remains. Nitrate, well, we have a nitrate here and here. Perfect. The nitrate we can cancel. So that's one of our spectator ions. What about the sodium? Well, we see sodium here, and we also see sodium there. So the sodiums we cancel. Very simple. And then the carbonate, we see no aqueous carbonate here, so we leave the carbonate. Okay, so the 2 spectator ions are the nitrate and the sodium. So the right answer for number 7 is C. Now, let's go ahead and take this opportunity to exercise this. Once we have canceled our spectator ions, we can write the net ionic equation. So this here is the complete ionic equation. If we wanted to write the net ionic equation for this, then that would just be 2 silver ions in the aqueous form plus a carbonate ion, also aqueous, and that's going to react and form the precipitate silver carbonate in the solid form. Okay, and those are the ones that don't cancel. So this right here is what we will call our net ionic equation. Okay. Number 8 asks us to determine which of the following are likely to be soluble in water based on the solubility rules. And what we can do for this one is reference the table, the solubility table. So from the solubility table, which I have right here, our first choice is, I can't show both of these at the same time, so we'll just, maybe I can. Here we go. Our first choice is, there, I'm able to get all of it in there. Lead sulfate. So let's see if lead 2 sulfate is going to be one of them that is soluble. So we come over here to our table, we look at lead, and we come over to combining it with sulfate, and we see that it is insoluble. So lead sulfate is not soluble. How about tin carbonate? Well, we don't have tin in the table, but we know from our solubility rules that just about anything with a carbonate is going to be insoluble. So, and we sort of see that here. The only things that are soluble with carbonate are like your sodium, potassium, maybe lithium, and also ammonium. So those are the ones that are soluble. Everything else here is going to be insoluble. So that's one of the solubility rules, that just about anything with carbonate is going to be insoluble in water, so that's not soluble. And barium nitrate, well, barium, and then we're going to combine it with nitrate. Barium nitrate is soluble. So barium nitrate is one of the ones that is soluble. And ammonium phosphate, here's ammonium, and we're going to come down here with the phosphate. And lo and behold, ammonium phosphate is also soluble. So the answer for number 8 is C and D. Now, for number 9, which of the following reactions in aqueous conditions would form a precipitate? So for these, what you would need to do is you would need to write out the double displacement reactions for each of these, and see if you make an insoluble product. Or you could just recognize that when you're writing a double displacement reaction, you're just switching partners. So you might just even be able to go like this. Nitric acid combining with copper sulfate, copper 2 sulfate to be specific, is going to make copper nitrate and sulfuric acid. Okay, copper 2 nitrate and sulfuric acid. So is copper nitrate one of the insoluble molecules? No, it is not. Copper sulfate is indeed soluble in water. So that is not going to be one of the answers. Sodium hydroxide this is a strong acid, and sodium hydroxide is a strong base. Immediately you might recognize that this is an acid-base reaction. In an acid-base reaction, doesn't really matter what the acids and bases are, you're going to make an aqueous salt and water. So, well, that doesn't involve a precipitate, so it's not going to be B. C is the same thing. We have sodium acetate and HCl. So in these situations, you can do the double displacement. You realize that you get acetic acid and sodium chloride. Both of those are very soluble in water, so that's not going to be right. And the only one that you're left with is D. And you would make mercury phosphate as as one of your products. And we can confirm this with the table where we have mercury here. There it is, mercury. We come over to the phosphate. There it is. And our mercury phosphate molecule is indeed insoluble, so that would be a precipitate. So for number 9, the correct answer is D, because one of the products with this reaction when we do a double displacement is a solid. It does not dissolve in water, and that would make it a precipitate. And lastly, what is the net ionic equation for the reaction between HCl and calcium hydroxide? Well, let's see here. HCl is a strong acid. So HCl is a strong acid. And calcium hydroxide is a strong base. It's a strong base. And if I can just take a second here and we can look at this table. This is a table that shows the strong acids and the strong bases. Hydrochloric acid is one of the strong acids. And calcium hydroxide here is one of the strong bases. Alright, so now we know we got an acid, we know we have a base. When they combine, are they going to make a precipitate? No, they're not going to make a precipitate, right? Because you make a soluble salt, it's going to be aqueous, and water. So that immediately eliminates all of the options here that have us forming a solid product, right here. This is a solid product, so the answers cannot be C or D. Alright, so let's take a look at B here. We got H plus and hydroxide combining, but well, this isn't even a balanced equation, right? So you get calcium and chloride, but where are the calcium and chloride here? It's like we've destroyed the calcium and chloride. Where did they go? Well, so that's obviously not going to be a valid equation because we don't have all the atoms that we started with over here in the products. So that's not going to be correct. And that leaves us with hydrogen and hydroxide combining to make water. So the correct answer for number 10 is A. If you wanted to do this a little bit more systematically, instead of like a process of elimination, you would just do H plus. Right, I'm going to go ahead and just split these apart. And chloride, they're going to combine with calcium. And I've got 2 hydroxides. Okay, and all of this is aqueous. And it's going to combine to do a double displacement reaction to form the ions calcium, and chloride. And there's going to be 2 of them, right? Because I need 2 chlorides to combine with the calciums. So if I need 2 chlorides on the products, I also need 2 chlorides in the reactants. And 2 protons, because I get them from HCl. And now I make liquid water. Oh, let me just be specific. This is aqueous chloride, and now I make liquid water. Water is not aqueous. Water is what everything is aqueous in. That's what aqueous means. It means that things are dissolved in water, and so water is our liquid. So water is just left as a liquid. And to make sure we're balanced here, we've got 2 oxygens and 4 hydrogens, so we're going to make this a 2 right there. And now our reaction is balanced. We cancel out the spectator ions, like this, and the net ionic equation we're left with is 2H plus and 2 OH minuses. Okay, and that's going to produce water in liquid form. So this is the characteristic net ionic equation for an acid-base reaction. So if you wanted to go through this systematically, you would determine that this is your net ionic equation, and so that corresponds to the correct answer for number 10 being A. All right, there you go.